Today we are discussing problem number 42, which is this recent advanced paper question on simple harmonic motion. Statement of the question you can see on the board. I will briefly describe what is given. There's a spring whose one end is fixed on a circular ring. The whole system is vertical, in the vertical plane. One end is fixed, the other end is attached to a disc. The disc can roll without slipping on this ring surface, edge. Spring is coiled through the ring so that when the disc moves, either the disc moves to the right means that there will be elongation of the spring, and if this disc is moving to the left means compression will take place. So if you in the equilibrium, the disc is at the lower end of this, is given here. Periphery disc is the equilibrium, it is the lowest point. So when you disturb, it will undergo angular simple harmonic motion. So what is there will be some time period will be attached to it, which is given by 2 pi by omega. Omega is the angular frequency. That omega we have to work out. There are this ring has a radius capital R, and the disc has a small r radius. So two radius are involved. So as the disc moves and when oscillation takes place, what is the angular frequency of the oscillation? Equilibrium, this is at the bottom of the ring. So that is this point. I am going to use energy conservation concept to solve this. That may be probably the easiest way of doing this problem. So energy conservation. Now we assume that it is displaced through an angle theta. This theta which I have marked on the diagram, which gives an elongation to the spring of equal to x. And due to that displacement, this is having a velocity v at that instant. And also due to which the disc has risen up by a vertical height h. So all these are marked, x, v and h are marked. So in terms of this, the energy equation is due to the spring elongation, spring energy is half kx square, elongation x square, plus this disc is undergoing pure rolling. So rolling disc, there is a total energy, kinetic plus potential. The total energy is involved. That means kinetic energy plus rotational kinetic energy, translational kinetic energy. So translational kinetic energy, rotation, total kinetic energy you have to make use. 3 by 4 mv square. That is the total kinetic energy of the rolling disc. Plus potential energy. Potential energy is due to the vertical rising, which is given by height h. So that will be mgh. Mass of this ring is, mass of the disc is m. So mgh. Mgh will be the gravitational potential energy. Total energy is given by this, which is a constant. So constant. Based on that constant only we are proceeding further. Now here where each of this quantity has its the symbols. Where x is equal to, where x is equal to r times theta. That is the circular motion concept. R times theta, x equal to r theta. V is equal to, r, not r theta, r minus r theta, because effective radius we have to take. We have to take out of the effective radius. So it will be r minus r theta. Small r theta. V is equal to r theta dot, omega r is omega equal to theta dot, d theta by dt. So r theta dot, r minus r theta, r because radius, effective radius is r minus r, theta dot. And x is, x is there, h is given by h equals, vertical height is original distance from the center is r minus r cos r minus r. Final distance is r minus r cos theta. So it will be 1 minus cos theta. So these are the quantities involved. X, V and H are given here. So we now substitute and proceed further. I will clear the board for further steps. Let us continue from the steps. I have written the expression for the variable quantities. X is equal to r minus r into theta. V equal, that means x equal to angular displacement into radius. Then V linear velocity is equal to omega r, where r is r minus r, into theta dot. Then h is equal to r minus r, being the effective radius, 1 minus cos theta, which I already explained. So that is, those are the. So now we substitute these variable quantities in the energy equation. Energy equation we have already done, half kx square, half k, x square means this x, r minus r square into theta square, plus 3 by 4 mv square, 3 by 4 m, v square means r minus r into theta dot square, plus mg into h, mg, h is r minus r, 1 minus cos theta. This is equal to constant. Now differentiating with respect to time. Differentiating with respect to time. With respect to time. Theta becomes theta dot, d theta by dt. Theta dot becomes theta double dot, like that. This also to differentiate. So differentiating with respect to time of k, r minus r square into theta square becomes 2 theta theta dot, plus 3 by 4 m, again r minus r square, 2 theta dot square means 2 theta dot theta double dot, theta dot square differential of it with respect to time, plus mg r, r minus r, 1 minus cos theta, differential will be sin theta theta dot. This is equal to 0 because sin theta theta dot, we are only concerned with small angular displacements. So Sine theta and theta are equal according to trigonometric concept. Sine theta. So this sine theta here written, you can just simply take it as theta. So theta is there equal to 0 we are getting. So differentiating. Then simplify this of k. Okay, of you can cancel. Okay, this 2 and 2 cancels. R minus R square, etc. cancels. So we get this will be here 2 also cancels. This 2 also cancels. Here also 2 cancels like that. So we get k R minus R square plus theta dot you can cancel everywhere because that is common. Theta dot we cancel. Here also all 3 cases. So k R minus R square theta plus 3 by 2 m R minus R square theta dot goes, so theta double dot is present, plus mg R minus R theta dot into theta equal to 0. So we have 2 types of terms with one involving theta, another involving theta double. This is exactly what we want for a simple harmonic motion, and this is the case of angular simple harmonic motion. So from this, if you further simplify, you get minus 3 by 2 m r, we divide by r minus r square, so theta double dot is equal to k plus mg by r minus r, mg by r minus r into theta. So theta double dot we are retaining here with a minus sign, remaining we take it to the other side. So theta double dot becomes equal to this, the theta double dot becomes some constant times theta. This constant, what we are going to get as constant is our omega square. So further I will continue after clearing the board. So from here we get theta double dot equals minus 2 by 3 minus 2 by 3 m k plus mg by r minus r into theta. So as I said, this is our square of the required angular frequency. So the last steps I write here. Or you can say this represents a angular simple harmonic motion. This represents an angular simple harmonic motion. Simple harmonic motion. Although I didn't use that angular word in the title, but this is when angular displacements are involved, it is angular simple harmonic motion with omega square equal to omega square equals this quantity 2 by 3. Okay, I will write it as 2 by 3 k by m plus g by r minus r by dividing by m. That is the omega square value. So k by m. So square root of this will be the answer. So required angular frequency is, this implies omega equals, okay, let me rewrite it. Final answer I will write as omega equals our required answer 2 by 3 K by M plus G R minus R. Square root of the whole thing. So this is the required answer. So I believe you followed the steps on deriving this. This energy concept was used, which is comparatively easier approach, I believe. So if you understood, well and good. Thank you.